Okay, folks, so as promised, now we start to look at what's happening at the synapse. So I want you to imagine where this is a computer generated picture here, but sorry, checking one thing. I'm not ready to see that yet, sorry. Go back, it's not going back, let's go back here. I want you to imagine this is a zoomed in shot of two neurons connecting. So this would be a zoomed in shot of a terminal branch at the end of an axon. And this would be the terminal button or terminal knob or bouton. And these little green circles are representing neurotransmitters. Remember, those are the messages that are going to be sent from one neuron to the next. Okay, so this down here represents a dendrite. A dendrite connected to the cell body, reaching out, connecting to an axon terminal button so that these two different neurons can communicate together. You've already seen my drawing. Brace yourself. Here's my attempt at a PowerPoint drawing of that same picture. We're also same thing, just zooming in even more. You know, don't blink because you don't see a difference here between this picture and this picture. Sorry, it's whatever. But here, let's break down the labels here. This is the axon terminal branch. Okay, now back up a second. This whole area here is, didn't mean to put that arrow there yet. This whole area where an axon meets up with a dendrite, okay, we're keeping it simple, where an axon meets up with a dendrite, this whole area is called a synapse, okay? A synapse, in other words, is a connection between two neurons. That's what a synapse is, it's a connection. Now notice the two neurons don't touch. There's a little space here, folks. The space is not the synapse. The space is called a synaptic space, also known as a synaptic gap. Tell me if you've heard me say this before. Psychologists are jerks. They make up different names for the same daggone thing. So this space here, where's my cursor? This is the synaptic space or synaptic gap, or even, ultimate jerkiness, the synaptic cleft. Same thing. It's just a little space between where the two neurons connect. We say they connect, but they don't actually touch, okay? The synapse, and I'm going to do this. Here's more body modeling for you. I do it this way. If we were talking in class, like this whole thing is a synapse, right? If my arm now, this arm is an axon terminal branch, and here's an axon terminal button. That terminal button meets up with another neuron's dendrite, okay? So this arm's a dendrite. So we got axon, terminal button, meeting up with a dendrite. This whole thing right here is a synapse. It's a connection between two neurons, and that always happens from axon to dendrite. This is a synapse, and that's what we're looking at here, okay? So this is our terminal button, as we know, and everything up here is presynaptic. Everything before the connection point is presynaptic. Everything down here is postsynaptic. It's all relative, of course. Now, some stuff we haven't gotten to yet. These circles here, these sacs, are synaptic vesicles. This is the place where neurotransmitters are stored. So I've used geometric shapes to represent different neurotransmitters. Reminder, we said before, a neurotransmitter is the message that one neuron is going to send to another, okay? Sender, receiver, sender, receiver. And the neurotransmitters are the message that's going to be sent. Maybe you can see where this is all going. All right, now I use different geometric shapes and different colors just to represent the idea that there are different neurotransmitters in the brain. I don't even know if it's technically accurate. I think research is still being done on this. For one neuron to hold multiple neurotransmitters like this, that might not be factually accurate. It may be. There's some research suggesting that some neurons contain more than one neurotransmitter. We could imagine maybe this neuron just has red triangles. Not actually red triangles, but let's say, I don't know, red triangles, that's, I don't know, that's dopamine, a neurotransmitter maybe you've read about already. And maybe the yellow circles are endorphins, which we'll talk about in a little bit. The blue squares are serotonin or squaretonin. Am I right? Squaretonin. You see what I did there? Shut up. Okay. Anyway, different neurotransmitters exist in the brain. Each neurotransmitter just carries a message. We'll get into that in a little bit. Okay, let's go further in our model here. Down here, we've got a dendrite, a receiving dendrite, a postsynaptic dendrite, and all over the dendrite, I've kept it simple on the drawing here, all over the dendrite are these receptor sites. Okay, receptor sites, we've already said the dendrite is the receiving part of a neuron. Well, this is why, because you've got receptor sites littered all over the dendrites, just waiting to catch neurotransmitters. Now, as you can see, we've got triangles, circles, and squares to represent different neurotransmitters. And down here, we've got squares, triangles, and circles to represent the different receptor sites. I got to keep saying, I'm keeping this simple, but it's believed generally that the neurotransmitters and receptor sites work like keys and locks, meaning certain neurotransmitters can only fit and engage certain receptor sites. So these red circles are going to float down here into the synaptic space and fall into receptor sites to do their job. But the triangles, dopamine, are only going to go into the dopamine receptors. And endorphins are only going to go into the endorphins receptors. The squaretonin can only make magic happen in the serotonin receptor sites. Okay, now look, maybe an endorphin falls into the serotonin receptor site, but it's not going to do anything. It's not going to engage anything there. Key, lock, neurotransmitter, receptor sites. Okay. All right, I know this is deep and it gets confusing, but here we go. More on this same model. We have to know that all these neurons, folks, are littered with ions. Okay, ions are just chemicals with an electric charge. Okay, we've got an electric charge, and with neurons, the two most important ions we have to know about are sodium ions and potassium ions. We won't get too deep into this, but I do want you to notice, because it'll help make everything else make more sense. Sodium ions start on the outside of the axon membrane. Sodium ions start on the outside. I don't think you need to know that for the AP test, but a kid a few years ago, her elaborative rehearsal way of remembering this was SO. Sodium starts outside. Or my cursor. SO. Sodium starts outside the neuron's cell membrane. And you should imagine the sodium goes all the way up the axon, all the way to the cell body, maybe even around the dendrites. There's sodium ions all around the outside of the neuron. In the inside of the neuron, there's a bunch of potassium ions. And I've colored them yellow because bananas are high in potassium and sodium's white because that's salt, but anyway. So just realize we've got sodium and potassium ions that are opposite each other. Sodium on the outside, potassium on the inside of the neuron. So when this happens, the sodium ions make the outside of the neuron positively charged. Remember, we said an ion has an electric charge that it carries. Don't get too bogged down in these details. Just let's focus on sodium ions carry a positive charge on the outside of the neuron, and potassium ions have a negative charge, or they're with a negative charge on the inside of the cell. Quick detour for the bio experts. All by itself, potassium is positively charged, but there's a bunch of chloride ions that outnumber potassium on the inside that carry a negative charge. Anyway, again, we don't need all those details. Let's just know the outside of the neuron starts with a positive electric charge, and the inside of the neuron starts with a negative electric charge. We need to know that because this means that the neuron is polarized. Okay? That's a synonym for the neuron being at resting potential. The neuron is at rest when it's polarized. We've learned this term before, polarized. That means there's two opposites, right? Like group polarization. We learned about how somebody could have very conservative and somebody else very liberal ideas that become even more extreme when those people are around like-minded people, right? Group polarization makes those political ideas even more different, more opposite. That's what polarization is. It's oppositeness. Hot, cold, polar opposites. North, south, polar opposites. Here, positive, negative, polar opposite charges that exist in a neuron. This is when the neuron is at rest. When the neuron's resting, these ions are just chilling. Let's imagine they're set up, they're ready to fire, they're ready to move, they're ready to go, but nothing's happening yet. The neuron is at rest, but it's not going to stay at rest. This neuron is going to be stimulated. Maybe another neuron will start bombarding that neuron with its neurotransmitters, stimulating it with messages. Maybe it's because we stubbed our toe and a pain message is coming into the brain. Every neuron has a threshold of excitation, folks. And that threshold of excitation is, you ready for this? The minimum amount of stimulation needed, to make a neuron fire, to make a neuron go to action potential, to stop resting and start firing, bazonking. Sorry, I'm going to keep saying that. It's a fun noise. Okay, so say again, every neuron has a threshold of excitation. That's a threshold that it takes to make that neuron fire. So if that neuron is stimulated, let's go back again. If this neuron is stimulated a little bit, way up here at the dendrites, it's not going to fire yet. Nothing's going to happen to these ions until this neuron's, where are we at? This neuron's threshold is met to make it fire. Just like go down here. When these neurotransmitters are released, it's going to stimulate this neuron. But these few neurotransmitters might not be enough to make this neuron fire, to go into action potential yet. Think of it like this. I'll go ahead again. Think of a neuron like, it could be like a lot of things, but let's go with a mouse trap. A mouse trap also has a threshold of excitation. Imagine a mouse trap being set. I don't know what to do with my hands there. It's not a good mouse trap symbol, but that mouse trap is set, right? If you've ever used a traditional mouse trap, you set it, right? And it's got this trap on this end. And if you stimulate the trap, the bait part, if you push on it just hard enough, it'll make the trap itself snap down. But imagine, okay, the mouse trap is set, it's ready to go, it's ready to snap and do some damage. You could blow on the trigger, but that's not enough stimulation to make the mouse trap snap. The mouse trap is like a neuron in that sense. Every neuron has some level of stimulation that it needs, that's not enough, to make that neuron do its job, to snap, to fire, okay? That's not enough to make a mousetrap fire, but if I put a little beard hair on the mousetrap, maybe, no, not enough, no, not enough stimulation on the mousetrap. This is weird, I know, bear with me, right? But if my chin scrapes the trigger hard enough, the mousetrap is gonna snap and jack this mug up even more, right? Same thing with a neuron. If one neuron is being stimulated it takes a certain amount of stimulation, a certain amount of neurotransmitter bombardment to make a receiving neuron do its job, fire. Okay, so let's see it happen. Imagine what I'm about to show you has already happened way up the axon, up around the cell body and the dendrites, okay? Here we go. If this neuron, where are we at? If this neuron is stimulated to its threshold, then the sodium ions are going to move inside the cell membrane, okay? At the sodium-potassium pump, the sodium is going to move in, and now that part of the neuron is depolarized. Remember, polarization is when, look here, the sodium and potassium ions are separate from one another on opposite sides of the cell membrane. But depolarization is when these ions start to mix. They're no longer separated. Okay, the sodium rushes in, that's depolarization. The cell is no longer at rest. Okay, these ions are no longer chilling. The neuron is now in action potential, and let's look at what that means. This is cheesy. Get ready. You ready? Boom. Crack-a-lacka. Look at this. The sodium rushes inside the cell membrane, and I'll say it again, to keep it simple, it causes a tiny explosion, a tiny electrical spark, a surge. Think of it like this, okay? Let me go back one slide. Let's go back to polarization. Where were we? Here we go. This neuron is polarized. Let's imagine, I'm big on metaphors, you guys know that. Let's imagine I've got jumper cables hooked up to a car battery. Don't try this at home. Don't play around with car batteries and jumper cables. I've got jumper cables hooked up to a car battery, okay? Imagine I'm holding the terminals from those jumper cables, okay? I've got the positive terminal in my right hand. It's usually red on a set of jumper cables. And I've got the negative cable in my left hand. All right, think of it as those cables have an electric charge running through them, a positive charge, like sodium here, and a negative charge, the potassium. As long as I keep those two terminals, those cables, separate from each other, I've got polarization. Nothing weird is happening here. But if I were to bring those two clamps together, if I bring the positive, again, don't try this at home, crazy dangerous. If I bring the positive jumper cable end together with the negative end, that's going to cause all kinds of sparking, okay? Could make the battery blow up. Don't play around with jumper cables, seriously. But anyway, okay, you bring the positive and negative together, you polarize, sorry, I messed up. You depolarize these two things, and there's going to be sparks, okay? Sparks will literally fly. And that's sort of what's happening inside the neuron. Depolarization, action potential. This is the beginning of, you guessed it, right? Little explosion, little tiny explosion. Now, watch what happens. And don't judge me for how long this animation took me to do on PowerPoint. There's a chain reaction once that starts to happen, which is the action potential. You're about to see the action potential continue down, imagine, down the whole length of the axon like we saw before. If it's got a myelin sheath on it, it's leapfrogging down the axon, right? Here's what it looks like in super slow motion, given my imagination and PowerPoint animation skills or lack thereof. Ready? Look at that. Holy crap. Oh my goodness. Oh wow. It's much faster than this in real time. But again, let me pause it there for a second. Pause. What are you doing? Pause. Stop it. Okay. Let's go back just a little bit. Notice the chain reaction that's happening, okay? The sodium ions rushed into the neuron. And imagine, this is happening all around the axon. When the sodium jumps in the axon, it forces potassium out. Okay, so let's go down to where we left off here. Sodium jumped in, potassium came out, which forced more sodium in the neuron, which forced more potassium out. So all along this chain reaction, we've got continued depolarization, right? Look down here, the end of the line, we've still got polarization like we saw before, sodium on the outside, potassium on the inside. But we're seeing the depolarization continue down the length of the axon. That causes this little explosion to run down the axon. Folks, this is the bizonk in super, super, super slow motion. So we see it again. This is the bizonk. Bizonk. Potassium out, sodium in, potassium out. They're trading places along the axon membrane, sodium and potassium ions, and every time that happens, the explosion, the spark, the impulse is carried down the length of the axon. Okay, now watch what happens next, and you'll forgive me for the rest of the stupid sound effects that I'm about to use. Ready? See if you know what happens here. Come on, where are we done? Okay, go. Bizonk happened all the way down the length of the axon. Now watch this. Blink, blink, blink. That was a little fast for me. Try again. Ready? Let's go back a little bit. We saw the neural impulse, also known as the action potential, also known as depolarization. I'll say that again. Depolarization is what we're seeing happening down the axon here as these ions trade places. Depolarization is also known as action potential, which is also known as the neural impulse, which is also known as a neuron firing, which I've been calling bizonk. Okay? Watch what happens when the bizonk ends at the end of the line. Neural impulse continues, bizonk, and then plink, 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 plink. Let's watch that in slow motion at the end. So, okay, so what we see here was, where are we at? Come on. Let's go here, and look at that. Now, I only released one vesicle's neurotransmitters here in my animation, again, to keep it simple so you can see what was happening. But you need to imagine, whenever a neuron has its impulse travel down to the end here, that causes all of these neurotransmitters to spill out into the synaptic space and end into dendrites receptor sites. Okay, so we're seeing what we saw, what I mentioned before. The endorphins go into the endorphins receptors, serotonin goes into serotonin receptors, dopamine goes into dopamine receptors, and then something else happens. But hold on, to finish this point, folks, this was it. This was the job of these neurotransmitters. The whole job of these neurons is to send and receive messages. And that's what we're seeing here. The neurotransmitters are the message. Okay, each one of these little chemicals carries a message, which we'll get to. And we just saw that message received into receptor sites of the postsynaptic dendrite. Okay, now job's done. These neurotransmitters have done their job. They've carried their signal, whatever that message is, to their destination. Now they're going to go back home. And again, this is very simplified. Some of these neurotransmitters are broken down and disintegrated. But again, keeping it simple, we'll go back. Every neuron will release its neurotransmitters. Those neurotransmitters go into the receiving dendrites, receptor sites, and then these neurotransmitters are going to be released, and many of them are going to go back to where they started. They're recycled later. You know what I mean? These neurotransmitters don't stay here. They don't absorb into the neuron and get passed on somewhere down the line. The key goes in the lock, and then the key goes back in the pocket. That's how neurotransmission works, very simply put. Okay, when that happens, check it out. That's called reuptake. Reuptake is the reabsorption of neurotransmitters from these receptor sites. Reuptake. Reuptake is when the neurotransmitters leave the receptor sites and go back to the sending neuron from whence they came. Okay? From which they came? Anyway. So I've got 4 cheesy sound effects there that might help you along with this process. Again, they were bizounc, plink, 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 bizounc, plink, plink, plink. I don't know why I repeated that. You could have gone back in your video player and play that again if you really wanted to hear it again, but a quick recap of what those sounds mean. Bizounc, that's the action potential, the neuron having its neural impulse travel down the axon. Bizounc. Then that's the sound of neurotransmitters being spit out into the synaptic space. Neurotransmitters falling out into the synaptic space. Plink, 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 plink. That's my stupid sound effect for the neurotransmitters falling into receptor sites. Okay? Destination reached. And then reuptake. Those neurotransmitters go back to where they came from. One more time. Ready? Bizounc. And plink, plink, plink. Stupid. But if it helps you learn how neurons work, I'm all about it. Okay? That's reuptake, the last step of the process. Okay. I'm going to stop there for now. That was a lot.